Good morning, everyone, and welcome to our talk titled Benchmarking Foundation Models, Inference Optimizations on Kubernetes. I know it's a mouthful, but we'll break it all down in the next 30 minutes. So about your speakers, I'm Sachin Varghese. I'm a lead machine learning engineer at Capital One. I'm also a workstream lead at the Linux Foundation's GenAI Commons.
And I'm Brendan Slabe. I'm a software engineer at Google on GK's AI Inference team.
So a disclaimer that this talk is not about proprietary models or optimizations at Capital One or Google, but rather structured around an open source project that myself and Brendan have been working on. So with that, let's get started. So the topics for today, we'll talk about GenAI models, an intro, like a primer on model inference. We'll talk about a few different optimizations if you are deploying or hosting LLM models on your own systems. Finally, an intro to a benchmarking tool and for validating the performance gains from these techniques, and also some example results, and finally, our path forward. So foundational models are at the heart of generative AI. These models are trained on large data. They learn complex patterns and generate content. This could be text, audio, images, or any other forms of data. This generated content then forms the solutions for many generalized problems like question answering, sentiment analysis, or even automating agents. So let's understand how these foundational models work under the hood. Here we consider text-based autoregressive models, so text in, text out. These models usually generate one token at a time. For simplicity, we can imagine these tokens to be equivalent to an English word in this graphic. The model inference itself has two stages, the prefill stage and the decode stage. The prefill processes all your input text or tokens and generates a single output token. And the decode stage generates subsequent tokens, one at a time, in an autoregressive manner. This entire process is hugely accelerated by the usage of a KV cache that stores results from previous computations for the next token generation step. The two key metrics that we would use to measure the efficiency of this process would be the time to first token and the time per output token. These are the two latency metrics that we'll try to optimize in the next few slides. Now let's consider the same inference process in a real-time production system handling multiple concurrent requests. Given the computational difference between these two stages, we can employ a static batching to combine the prefill and decode stages from various simultaneous requests. The prefill batch will be processed first, and then the decode stage begins. So when a new request arrives, it will be queued and processed only after the existing decode stage have been completed. This optimizes time per output token, but the time to first token increases due to the additional queuing time. In the same scenario, where the batch requests have a different output token lengths, the decode batch can be extremely inefficient in terms of hardware utilization, even with high number of concurrent requests, basically because the new requests are waiting. This is particularly a drawback in case of large foundational models, considering the high-end, expensive hardware that is used for inference. And you don't want it to be underutilized. So how do we solve that? This is where continuous batching, that is the ability to batch at every token generation step with a prefill-first approach, comes in. When a new request comes in, now the decode batch is interrupted, and the new prefill batch is prioritized without any queuing. The interrupted decode stage are continued in the next cycle. Unlike static batching, with this mechanism, the GPU utilization can be improved with more concurrent requests. Further, this optimizes time to first token due to the prioritized prefill, but the interrupted decode stages leads to higher average time per output token. Most inference servers today, the VLLM, TGI, you name it, most of them use some form of continuous batching. So can we get the best of both worlds? So this is yet another technique where instead of processing the entire prefill in a single step, what if it can be distributed over multiple chunks? So with this optimization, the concurrent decodes of other requests can produce one output for every prefill chunk instead of just one token output for the entire prefill phase. Thus, chunk prefill improves hardware utilization as decode stages can now be combined with shorter prefill chunks. Larger chunk size will optimize for time to first token, and a smaller chunk size will optimize for time per output token. So basically, your chunk size configuration acts like a knob for you to choose which metric to optimize for. Apart from tuning the efficient batching and utilizing the most performant kernels, post-training quantization can be very effective for reducing latency. Quantization uses low-precision model values for less computation and reduces the model memory footprint. Consider a 20 million parameter model. An 8-bit quantized version only uses a quarter of the GPU memory to even load the model compared to a full precision variant. With lower models, they have the lower latency due to less computation, but any form of quantization is a lossy compression, right? And that will have an impact on model performance. Most techniques hence require calibration and accuracy benchmarking to validate the efficiency of quantization for the specific use case in context. So next, we talked about quantized models or smaller models in general being faster, but they struggle in terms of accuracy in comparison to bigger models. Speculative decoding is yet another technique that pairs a larger model with a smaller model or a lighter draft mechanism to propose many tokens at once. So in step 1 here, the draft model is generating quickly many tokens. And then in the step 2, the original model verifies these proposals in a single forward pass, then accepts the prefix that matches its own predictions. If none of them match, it discards all the draft tokens to generate at least one new valid token. So basically, in a single forward pass, you generate at least one token, which is equivalent to the previous situation. So compared to model inference, this technique lets the system generate potentially multiple tokens at once, cutting the latency and boosting throughput without an impact on accuracy. But the efficiency of this technique depends on the ability of the draft mechanism to emulate the large model. There are many variants of this, like the n-gram look-ahead, Medusa heads, and eagle-based sampling. So we talked about many inference optimization techniques that improve the latency of the model without the need to upgrade the hardware. Now I'll pass it on to Brendan to talk about how we validate the performance gains from such techniques.
Cool. So back to inference perf. So why did we build this? The core challenge is that generative AI serving is generally a black box. So even a lot of the optimizations that Sachin was talking about, the specifics of how these affect performance you'll generally see diminishing returns as you start to look into these with more detail. So given that we're seeing explosive demand with generative AI serving solutions, and there are generally a growing number of choices for model servers, tunings, and serving stacks. The thing that we identified was that there's no clear standard way to evaluate performance, which makes it complex to compare options. So the result is that deciding on a serving stack is a very expensive task. So that's the gap that we're trying to plug with inference perf. And again, this diagram shows a bit about the architecture. So on the left, we have an API. We have an API that takes in it takes the form of a config file that just takes in your data, like the data sets or like your input data sets, your traffic patterns, anything around your model server config. That all goes into that one single config file. That's used to configure your data generation. So you're choosing/filtering the set of requests. Your load generation. So that's responsible for determining the URL, to either identify/determine the URL of the production models of your production stack or the model server that you want to test. It also helps configure the request, like the request times, the wait times based on your on the load pattern that you specify, and then also metrics collection. So, and then finally, like we have an API for report gen. So you could specify the granularity of the reports that you get back. So diving a bit deeper into the load pattern. So diving a bit deeper into InferencePerf's capability for generating load. The first thing that we want to highlight is that it's highly scalable. So for those of you who are considering large-scale production inference deployments such as LMD and Dynamo, this is going to be of interest. We're aiming to generate different load patterns to test specific scenarios, such as like burst traffic, scaling up to and past saturation, which is the point at which the model servers you start to observe request queuing. And there's work ongoing to make InferencePerf able to handle more complex auto-scaling and routing situations. And again, like that's all specified. Like that's all you're able to specify that via the API. And with respect to data with respect to the set of prompts, we support inferring the set of prompts from either real-world data sets like SharedGPT, CNN Daily Mail, or synthetic data sets like Mock, which is essentially just the same prompt over and over again. Random, where you're essentially just a random string of tokens, or prompts with a shared prefix. And again, like to get even more granular, you can specify the exact input and output distribution, specify input-output length constraints, define distributions like Gaussian or fixed length, and provide the number of shared prefixes. So, given all this, what do we get back from InferencePerf? So how do we describe the performance? And the data we collected gets compiled into performance reports. So InferencePerf provides these reports at several granularities, a high-level summary, which is the metrics for all requests across the InferencePerf benchmarking run. You can get per stage metrics. You can optionally opt in to get requests to get data at a per request level. And the reports also do include request lifecycle metrics, which are metrics about the requests and responses as the user would observe them, and Prometheus metrics as like self-reported by the serving stack. And the request lifecycle metrics are the main data driving InferencePerf's model of serving stack performance, which is the latency throughput curve. That's that diagram off to the right. And this is what we'd consider an ideal example of a latency throughput curve. We're essentially plotting throughput and in output tokens per second against the mean time to first token. This is critical because it's showing like the performance under various loads, such as like pre-saturation and post-saturation, where you start to see request queuing, which you could see off to the right as the throughput levels off. And again, one thing to call out is InferencePerf is not for qualitative benchmarking. This is very much for a tool for performance benchmarking. So qualitative benchmarking is sort of out of scope here. Now, we can walk through a more practical example of like how you would use InferencePerf to evaluate variations of a VLLM deployment. So in this case, the experiment setup was pretty simple. We ran InferencePerf as a Kubernetes job. A side note here. InferencePerfs, we do support, like running InferencePerf locally and in cluster are both very well supported paths. We have documentation on this. It sent traffic to a VLLM service, which routed that to a single VLM inference server pod that hosted Llama 3.18b. And I think my battery just died. Thank you for bearing with us. Now we can go back to walking through like that example. So again, just to recap, InferencePerf as a job inside the cluster, single service routing to a single VLM inference server pod. Metrics are being collected by Google Managed Prometheus, and we are uploading all the results to a Google Cloud Storage bucket. And as for the load, we had a 128 token system prompt, so the shared prefix, and that's made up of randomly generated tokens, plus a 64 token user prompt made up entirely also of randomly generated tokens. And the output length the output length was what we specified was 64 tokens, and then we had specified a base case, and then we tested a series of optimization/variations of that base case. So using the V0 backend from an older version of VLM, enabling prefix caching and chunking, increasing the batch size, using dynamic quantization, and using speculative decode with an EO3 model. So next few slides, we'll be going over the results. So the V1 engine, this is what we're using as our baseline. So these are the model server arguments that we specified besides other than the defaults. GPU utilization 90%, max model length of 512, and max number of sequences of 128. And also note for this base case, we disabled prefix caching and chunk prefill. So and this is the shape of the shape of this latency throughput curve is what we expected. The latency throughput curve is the one on the very left. Again, like we expected, latency metrics like time to first token and time per output token to slowly increase until the load hits the max throughput. And at that point, latencies will rapidly increase, and that's sort of that leveling off and that knee shape that you see. First variation is the V0 engine. So we used VLM 0.9.0. Base case was 0.11. And again, we just specified that environment variable. We superimposed the old results in blue. The new results are in red. And again, like we expected performance degradation, and that's what we observed. Again, like a little bit of background, V0 to V1 for the move from V0 to V1 was a significant architectural change. So again, we expected improvements, and yeah, that's exactly what we saw. And yeah, just generally higher throughputs at similar latencies. And this is a good example of inference perf treating two separate serving stacks as black boxes with respect to comparison, since in cases like this where specific architectural changes are where the specific architectural changes that influenced these results may not be obvious or trivial. For the next experiment, we increased the batch size, so just increased max number of sequences from 128 to 192. And again, blue line base, red line, the red line is the new config. And the expectation was that increasing the number of concurrent sequences would improve performance. And we did see some, but we did see some. The gains were more marginal than we would have. They were more modest than we would have thought, or than we would have expected. And so that tells us that simply feeding the GPU more data by increasing the batch size couldn't force it to process faster because something else is the bottleneck, and that's more likely just doing the math itself. So this is hinting that the workload in the base case was compute bound. So for a more obvious improvement, we enabled prefix caching and chunking. Again, blue line is base, and again, the performance gains were much more substantial. The results were due in part to the characteristics of the load. Like remember back to the initial slide where all requests shared a prefix. So relying on the pre-computed KV cache values massively reduce the prefill time. And yeah, you can see that in the middle graph where time to first token is massively increased. Chunking also increased GPU utilization, which contributed to higher throughput overall. So peaking at around 10,000 output tokens per second, up from 6,300. And again, this is more reinforcement that the original workload was compute bound. Next, we tested in-flight quantization. So we used, again, base case arguments. We configured VLM to use the bits and bytes quantization, using the quantization flag. And again, we saw very similar results that we saw with the prefix caching and chunking. So again, a little bit of background: quantization allows for just faster computation on a compute. So on a compute-bound workload, we expect to see much more. We expected to see stronger improvements, and the data agrees with this. And again, one thing to call out here is even though we are seeing improvements in performance, we are deliberately ignoring the quality of responses because again, inference perf not a qualitative benchmarking tool. And then lastly, we tested speculative decode. So again, we just added the speculative decode config to our base case arguments, redeployed, and we set this number of speculative tokens equal to 4, and we just picked a random equal 3 model that wasn't fine-tuned for our use case. And in this particular case, we did actually see performance decrease, so which wasn't entirely surprising. So the expectation is that the equal 3 model would introduce overhead, which was known, but we didn't have any particular expectations around performance gains because we suspected the draft token acceptance, the next speculated the rate at which we are accepting the speculated tokens is going to be low, given the fact that the prompts that we're generating are essentially just random tokens. And that's exactly what we observed. So in this case, the overhead of running the draft model was greater than the savings from accepting the draft token. So this should demonstrate the impact of how a draft model can affect performance for your particular load and how inference perf can be used to evaluate more of these niche model server tunings, or picking a draft model. So as for our roadmap, we are planning to build a deployment API to help automatically deploy these different inference serving stacks for testing. Other features we're also working on, traffic routing for testing different model servers or LoRa adapters, adding multi-turn chat support, adding support for trace replay and support for real-world and for using real-world trace datasets. We also want to expand to multimodal benchmarking, so non-token-based inputs/outputs. So diffusion workloads fall under the scope of this effort, and improving accelerator metrics collection. And again, like it goes without saying, like one of our highest priorities is continuing to add support for more model servers, stacks, data sets, the like. And again, lastly, we just want to say this is an open source project under Kubernetes SIGs, and we want the aim of this project is to be the source of truth for inference benchmarking. And to that end, we're always welcoming new contributors. So for anyone who's interested, either copy down the link or scan the QR code. Feel free to try it out. And again, thanks to everyone for joining. And for anyone who's interested in learning a little bit more about inference perf, there is another talk going on in Ballroom 2 at 4:15. We have a few other contributors, including Jason Kramberger. Sachin and I work pretty closely with him. He's part of that presentation. They are presenting a more comprehensive tutorial on how to use inference perf for benchmarking. Right, so I think with that, we can move on to Q&A.
Thank you.
How does this work?
There's one. Oops.
I guess a question for you, like, are you just sort of like running these things from like your, oh, there we go. Are you running these from like your laptop to just like direct against like the GKE infrastructure and that sort of thing? Or are you using like other systems to kind of help, I don't know, manage the hardware and everything that's under the covers?
So you're asking about the experiment setup in particular?
Yeah, the experiments themselves, yeah.
All right. So the experiment setup was pretty controlled. It was essentially just an internal use only GKE cluster.
Gotcha. Okay. Have you guys looked at using some other tools to kind of help manage like lots of people running experiments simultaneously and that sort of thing? Like rather than just like, oh yeah, everybody gets a cluster to kind of deal with this and like batch them and queue them, that sort of thing?
We haven't, but we do make an effort to make sure that when you are running inference perf, when you have multiple inference perf jobs going at once, that the metric scraping is isolated. Making sure that there's no spillover.
Awesome. Cool. Thanks.
Hi. So if I understood your network architecture diagram correctly, instant perf is both running the test and then reading the output from Prometheus, or is it reading the metrics from Prometheus?
So it's automatically scraping metrics based on your particular model server or serving stack. Well, there's two categories. There's the request lifecycle metrics, which are calculated just based on the input length, output length,
Right.
like start time, end time, all that. And then again, Prometheus metrics are it's essentially just not an automated metric scrape.
Okay. Is there a hard requirement on you already having configured your Prometheus endpoint, or does this work in any Kubernetes native cluster?
So metric scraping is opt-in.
Okay, so it's opt-in.
Right. Yeah, and right now we support self-hosted Prometheus or Google managed Prometheus. Again, it's one of those we're just sort of looking for contributors for other managed Prometheus platforms.
Okay, all right. So there's a requirement that your cloud endpoint is having a managed Prometheus cluster, or that you configure your Prometheus endpoint within your siloed cluster, right?
Oh, sorry.
So there's a requirement that you're if you're running I forget what the AWS service is, but the AWS's native Kubernetes service, GKE on Google, or OCI's native Kubernetes service, those already have the Prometheus endpoints configured. If you're not running within those managed endpoints, you then need to configure the Prometheus server in order to run the instance.
Correct, yes.
Okay, cool, that makes sense. So, all right, so there's just, what I was getting at is there's a hard requirement that Prometheus is already enabled in order to run these tests.
So if you configured Inference Perf to scrape metrics, then yes, that's a requirement.
Okay, cool, thank you.
Sure.
All right, thank you all.